In this lecture, we are going to discuss the chapter 7, light. Light is just another kind of wave. We are going to study the source of light, some properties of light, means some phenomena that are associated with light. There are two kinds of source of light. If the source is luminous, then the object produces light, for example, the sun or the candle. But if the source is incandescent, then the visible light is given off as a result of high temperatures. For example, the bulb, and also can be a piece of metal that is at high temperature. Light waves are also called electromagnetic waves because they consist of electric and magnetic fields. The electromagnetic wave model is used to explain the nature of light. The electromagnetic wave model was first proposed by James Maxwell, and this model describes the relationship between electricity, magnetism, and light. The electromagnetic wave model displays electric and magnetic fields, and they are always perpendicular each other. Another important thing is the electromagnetic waves can travel in the empty space in vacuum. And mechanical waves, like for example sound and light electromagnetic waves, require the presence of medium to travel. For example, the sound wave required the medium like air or water or any solid in order to travel. And one more thing is any wave transports energy from one location to another. Now let's describe electromagnetic spectrum. Electromagnetic spectrum includes the entire range of light that exists, from radio signals to gamma signal or gamma rays. The visible part of the electromagnetic spectrum is just a small part, it's just tiny part of the electromagnetic spectrum, as you can see here. Yes, and in visible light we include all the colors. But we can see most of the waves of the electromagnetic spectrum are invisible for us. As we say, also the waves of the electromagnetic spectrum travel at the speed of the light in vacuum. Means all these different waves travel at 3.00 10 to the power 8 meters per second in vacuum. Because these are waves, then we can describe the motion of these waves using this equation. Remember, V corresponds to the speed, the lambda corresponds to the wavelength, and F for frequency. In this case, because these waves travel in vacuum at the speed of the light, which we use the symbol for C for the speed of the light, then we can just replace the speed by the letter C. Then the equation we can use to describe any of the waves of the electromagnetic spectrum is C equal lambda multiplied by the frequency, where C is the speed of light in vacuum, lambda corresponds to the wavelength of any of these waves, and F is for frequency of any of these wavelengths. And also we can see the electromagnetic spectrum consists of a complete range of frequencies. For example, high frequencies correspond to the gamma and X-ray rays, and low frequencies correspond, or small frequencies correspond to the radio signal. Also, we already studied the relation between the wavelength and frequency is inverse proportionally, but we can just review here again. This is the equation we can use to describe any of the waves of the electromagnetic spectrum. And if we divide by the frequency on both sides, this cancel out, then we will have wavelength equals, and we know the C is the speed of the light in vacuum. Then if we apply the line test, we can see the wavelength and frequency, they are inverse proportion. Means if the wave has high frequency, then they will have a small wavelength. Yes, but if the wave, like in case of the radio, has low frequency, then they will have high wavelength, as we can see in this picture. Another concept that is associated with the electromagnetic radiation is the blackbody radiation. Remember, the electromagnetic radiation is given off from any matter at any temperature. If the temperature of the body is higher than 0 Kelvin, then they will emit some radiation. That radiation is called electromagnetic radiation, or also is called blackbody radiation. For example, the body temperature of the human and animals emit in infrared region. Now, if the temperature is about 98 Fahrenheit, then we emit radiations that the wavelength is about 10 micrometers. That correspond to infrared region. Now let's talk about the properties of light. We can see objects if they are luminous, means if they emit light, or if they are non-luminous, if they reflect light. And one example of the luminous is the sun, and the non-luminous is the moon. The moon reflects light. We cannot see the path of the light itself, but if there is a dot that we had in this picture, we can see the path of the light, and we can see the light travel in a straight line. Then when the light travel in a straight line, what happens with the light when interact with some matter? Then what is going to happen depends on these three factors. One, depends on the smoothness of the surface, the nature of the material, and the angle that the light strikes the surface. Then let's discuss the first point, the smoothness of the surface. If the surface is perfect smooth, like we had in this case, the rays of the light undergo reflection, perfect reflection, and this reflection is called specular reflection. But if the surface is not smooth, like in this case, the light will scatter in many directions, in different directions, and in this case we will have diffuse reflection. Also depend on the nature, what is going to happen if the light interact with matter, depend on the nature of the material. If the material is transparent, then all lights pass through. If the material is translucent, then sunlight pass through, but sunlight is not going to pass. If the material is opaque, then the light is not passed through that material. What happens with the light when interact with the matter depends on the angle that the light strikes of surface. This is the third point. If the rays strike the surface at some angle, most of the light is reflected, as we can see in this pictures, and here we had a specular reflection, as a smooth surface. But however, most of the objects that we are able to see is because of the diffuse reflection. It's because there is no smooth surface. And we already studied the phenomenon associated with the sound wave. Then we are going also to study the same phenomena but that are associated with the light, which is a wave source. Then first start with the reflections. Reflection occur when the light interacts with the matter and it bounces off. Remember that when the sounds bounces off, when the sounds travel and hit some surface and bounces off, this phenomenon is the reflection of the sound, or we call echo. And now the same thing happened with the light. As if the light travel and hit some surface or some object, then the light will be bounces off. Here in this picture we had a specular reflection for one ray. The incoming light is called incident ray. Yes, it's just one. And the outcoming light is called the reflected light. The angle that we measure from imaginary line that is perpendicular to the surface, this line is called the normal line. The angle we measure from the normal line to the incident ray is called the incident angle, or the angle of incidence. And the angle that is measured from the normal line to the reflected ray is called the angle of reflection. Then what happened, as we can see in this picture, this is a real picture. We can see if we measure the angle of incidence, we can see the angle of incidence is about 50 degrees. And if we measure the angle of reflection, we can see the angle is 50 degrees. And we can see the angle of incidence and the angle of reflection, they are the same. Then the law of reflection states that the angle of incidence equals to the angle of reflection. Another phenomenon associated with the light is the refraction. Remember, refraction corresponds to the bending of the wave, and this occurs when the light moves from one transparent material to another. For example, from air to water. This is the examples we had in these two pictures. In the first picture, we have the light is moved from the air to glass. That happened because the light undergoes a change in the direction, and the change of the direction occurs because there is a change in the speed of the light in the two different mediums, like for example air and water. But the magnitude of the refraction depends on the angle at which the light strikes the material or the surface, the ratio of the speed of the light in the two materials. Yes. The third one is the ray of the light that is normal or perpendicular to the surface, means the ray that is in this direction, the ray that is in this direction is not reflected at all. Yes. If the incident ray is perpendicular to the surface, is not reflected at all. And in this case, we can see again, we had the incident ray, we had the refracted ray, and we had the imaginary line that is perpendicular to the surface, which is the normal line. Then we use the normal line to measure the angles, and the angle between the normal and the incident ray is the incident angle. but the angle between the normal line and the refracted ray is called the refraction angle. The index of refraction is a property of the material that correlates the speed of the light in vacuum and the speed of the light in that particular material. And the symbol we use to identify the index of refraction is the N. Then the index of refraction describes how fast the light travels in some particular material. Then the index of refraction is the ratio of the speed of the light to the speed of the light in that particular material. We can see here in this table we had the index of refraction of different material, and one thing we can see here is the index of refraction in air at 0 degrees Celsius or 30 degrees Celsius is really the same, and is about 1. Means if this ratio equals to 1, means the speed of the light in air is close to 3.0 10 to the power 8 meters per second. It's almost equals to the speed of the light in vacuum. And this is why in most of the problem, when we are talking about when the light is traveling in air, then we can take also the speed of the light as 3.0 10 to the power 8 meters per second. And one thing you can notice here, there is no units for index of refraction, as there is no units. It is a dimensionless number. And why this happens? And let's in SI system, then the units for index of refraction. On top we have the speed of the light, and the units is meters per second. In the denominator, we had the speed of the light in this particular medium, and this is also meters per second. And we can see the units cancel out. This is why there is no units in case of the index of refraction. Then let's try to solve a problem. Then what is the speed of the light in a diamond? And we know the index of refraction equals to the speed of the light over the speed of the light, in this case in diamond. Yes. And we want to know we want to know what is the speed of the light in this particular material. In this case, we need to know the index of refraction of diamond, yes, because this is the index of refraction of the material. Then in order to know that, we will see the table we had in our book, that the index of refraction of diamond is 2.42. Then let's write this number here, 2.42. And no units. And now we had all the information we need. Yes, we need this is a constant value. This is the speed of the light in vacuum, which is meters per second. The index of refraction is 2.42. And then we want to know what is the speed of the light in diamond. And we add equation, and we can just cross multiply, because we need to solve for the v, for the velocity of the light in diamond. And we divide by index of refraction, then we have c over then now we divide 3.00 10 to the power 8 meters per second, 2.42. And as we expected, the units for velocity is meters per second. Yes. And if we divide these two numbers, we will find the speed of the light in diamond is 1.10 to the power 8 meters per second. And this is the speed of the light in diamond. And one more thing is when you are calculating the speed of the light, you expected larger number. Yes, then don't forget the power of 10. Yes, when you are calculating the speed of the light in some particular material. And now we are going to discuss the Snell's law. Snell's law relates the index of refraction of the two materials, the index of refraction of this material and this material, and also the angles of the incident and the refracted rate. And in this equation, and in this case we had the index of refraction of the second medium over the index of refraction of the first medium equals to the sine of the angle of incidence over sine of the angle of refraction. What is sine? Sine is just a trigonometric function, and what we are going to do in our lab is we will use the calculator to find that number. Okay, then you don't have to think anything about more than that. It's just you will use the calculator to find that value. But what we need to know if we want to apply this we need to know at least one index of refraction. We need to know the incident angle, and we need to know the refraction angle. If one application of this law is you can find the velocity of the light in a medium that you don't know. If you don't know what is the speed of the light in some particular medium, you can apply the Snell law to calculate that. Then here we had one example, and this is the Snell law. If the first media is air, we know the index of refraction in air is about 1. Yes, it's close to 1, and we can consider like 1. If this equals to 1, then what happens is we can rewrite this equation in a simple way, because n2 divided by 1 is just n2. Then we can just rewrite this equation, and then if we know the incident angle and the refraction angle, then we can calculate the index of refraction of the second medium. Yes, we can calculate the index of refraction if we don't know. Yes, if we need to calculate this index of refraction. And we can use the equation of the index of refraction to calculate the speed of the light in that particular medium. Because we know from the Snell law, we can calculate the index of refraction. Yes, we will know this one. We will know this one because we can measure this angle and this angle. If we know this one, if we know the index of refraction, if we know the speed of the light in vacuum because it's a constant value, then we can solve for the velocity of the light in that particular medium. And this is one of the application of the Snell's law, and we will apply this equation in our index of refraction experiment. And we already discussed the electromagnetic waves. They travel at the speed of the light. This means 3.0010 to the power 8 meters per second. Because they are waves, we can use this equation to describe the motion of that waves. And that waves can describe by wavelength, frequency, speed, and also period, for example, because if we know the frequency, we will know the period of the wavelength. And this is the whole electromagnetic spectrum, and all these waves travel at the speed of the light, as from from gamma to radio signal. But let's concentrate in this part of the electromagnetic spectrum, in the visible part, is the part we can detect. And because all these waves belong to the electromagnetic spectrum, all the colors that now we know are waves travel at the speed of the light. Yes, all the colors are waves and they travel at the speed of the light. Means we can identify colors with some particular wavelength, with some frequency and some period. And all the colors in air and in vacuum, they travel at 3.00 10 to the power 8 meters per second. And we can see there is just small part, tiny part of the electromagnetic spectrum we can detect. Then the wavelength, the range of the wavelength we can detect, as the wavelength we can detect is from 400 nanometers, which correspond to the violet, to 750 nanometers, which correspond to the red line. In 1672, Newton found that the white light is a mixture of all these colors. Is the mixture of all these colors. Let's talk about the units of the wavelength of the visible waves. And let's start with the red. And we say the wavelength in case of the red is about 750 nanometers. And we know nano is a prefix, and we can also write ten to the power minus 9 meters. Remember, nano means 10 to the power minus 9. Also, another way we can write the same number, we can write this number in scientific notation. Yes, we can write this number in scientific notation. Then we can move 2 places, because we move to the left, we know we need to add. Yes, we need to add. Then we will 750. Let me write in scientific notation 7.50. Because we move 2 places to the left, we need to add. Then will be minus 9 plus 2 will be minus 7. Remember, we need to move 2 places to the left. We need to add 2 units to the exponent. That's minus 9 plus 2 will be negative 7. Minus 9 plus 2 equals to negative 7. This is the power of 10, as we had here. Then this is the 3 different ways we can express the wavelength for red. Yes. Then we can say the wavelength for red wave is 350 nanometers. For red also we can say is 750 10 to the power minus 9 meters. Or we can say also 7.50 10 to the power minus 7 meters. Then these are 3 different ways we can express the wavelength for red color. And here we had all the other colors, and we can do similar. You can express in the similar way. Yes. And you will have here, for example, orange. You will have here yellow, green, blue, violet. And let's for violet, and this corresponds to red. Yes, let me do something like that. Oh, it's not good. let's express for the violet. Then the wavelength will be 400 nanometers. Then we can express this one like 400 10 to the power minus 9 meters. Why? Because the prefix indicate 10 to the power minus 9. Or we can write this one like 4.00 10 to the power minus 7 meters. And these are three different ways we can express the wavelength for violet. And we know because all these waves, all these colors belong to the electromagnetic spectrum, then they travel at the speed of the light in air or vacuum. Meters per second. And let's now try to solve one problem. Then now we know the colors are waves. We can identify that waves with frequency, wavelength, and we will see later we can also identify that color with some particular energy. Then the colors are waves. And what happens is the human eye is most sensitive to light with the wavelength of 5.60 10 to the power minus 7 meters, which is in yellow-green color. This is between yellow and green color. And what is the frequency of this wavelength? And we know this is the equation. We can describe any wave, and we know colors are waves, then we can describe that color using this equation. And we know this is the speed of the light in air or in vacuum, which is almost the same. And let's see now what information we know. And we know the wavelength 10 to the power minus 7 meter. We know also the speed of the light 3.00 10 to the power 8 meters per second. We want to know what is the frequency. And let's apply the equation, because we need to solve for the frequency. We divide by the wavelength on both sides. And finally we had the frequency equals the wavelength. And the next thing we need to check if the units are consistent. Yes, are the units consistent before to start calculating? Are the units consistent? Yes, as we have meters per second, then no problem. And now we can just calculate the frequency. And 3.00 10 to the power 8 meters per second divided by the wavelength will be 5.60 power minus 7 meters. And here you have just be careful when you are doing the calculation, when you are dividing this. For example, if you divide the numbers and then you solve for the power of 10, and you should probably you will get this one 3, 6, 10 to the power 10, 8 minus 7, you will get 15. And let's see meters per second. And here we need to flip because we had division is 1 over meters. Yes. Then this cancel out. And let's write this one in scientific notation. And we move to the right 1. If we move to the right, we need to subtract 1 unit because we moved 1 place. And 15 minus 1 will be 14. Then if we write this one in scientific notation, then we move 1 place to the right. If we know if we move to the right, we need to subtract 1. Yes, it will be 15 minus 1 will be 14. And we can write this one like 5.36 10 to the power 14 1 over second, because meters cancel out. And finally, we can write this one also. We know 1 over second is hertz, yes, and this is the units for frequency. We can see the frequency of the yellow and green color is 5.36 10 to the power 14 hertz. That's the frequency for this particular wavelength. And we can see from this picture the only frequency of the electromagnetic spectrum that we can detect are the frequencies in which the power of 10 is 14. We can see here is the wavelength. We can detect from 400 to 750 nanometers. We already discussed that. But we can see the frequency correspond to 0.3 10 to the power 14 hertz to 7.5 10 to the power 14 hertz again. Then this is the only frequency we can detect from the electromagnetic spectrum is the frequencies in which the power of 10 is 14. And this is all I had to discuss today.